Hello everyone. Assalamualaikum warahmatullahi wabarakatuh. We are from group A2. Our group members are Muhammad Syazwan bin Muhammad Aziz, Muhammad Haris bin Mazlan, Muhammad Hafiz Hakimi bin Sa'rin, Muhammad Haziq bin Hazani, Muhammad Adam Ikmal bin Ahmad, and Rabiatul Adawiyah binti Mustafa. We are going to present about Stretchable Conductive ink. Project summary. This project is conducted to do a research on new substitute materials for development of new stretchable conductive ink SCI, which can enhance the mechanical and electrical properties. To produce SCI, we should follow the materials formulation of SCI, which are matrix materials, metallic fillers, and substrate materials. The example of matrix materials is PDMS. For metallic fillers are TPU and PET. Lastly, the example of substrate materials are silver and carbon nanotube. At the end of this project, we can identify the new substitute materials that are suitable to produce stretchable conductive ink, which can lead to a low production cost and has better mechanical and electrical properties to improve their performance. Background study. Numerous studies have been conducted to develop the next generation of high flexibility, low cost, and simple to manufacture printed conductive electronics devices. Printed circuit board PVC is the example of flexible electronic devices. The electrically conductive composites that are the key materials for printed conductive to be used in the field of printed conductive electronics devices are formed by the conductive fillers added to the mixture which form the electrically conductive composites. Stretchable conductive ink (SCI) is composites used to enhance the mechanical and electrical properties in the film on the PVC board after go through stretching and folding. SCI composites have added to the creation of strain sensors, health monitors, and antennas. Problem statement. Stretchable conductive ink using metallic fillers such as silver, carbon nanotubes, and graphene, matrix materials like PDMS, and metallic fillers including TPU and PET has been widely used in a range of applications. But from all the materials, which material may offer highly conductive, stretchable, and reliable at varying strain the temperature on flexible PVC board? Research study has conducted to suggest substitute materials for develop a new stretchable conductive ink. It is important to enhance the mechanical and electrical performance in addition of lowering costs needed to production of SCI. Definition of nanocomposites. Nanocomposites are heterogeneous or hybrid materials made at the nanometric scale by the combination of two or more separate building constituents in one material offers unique properties that plausibly arises from their small size, large surface area, and of course from the interfacial interaction between the faces. Their structures have been discovered to be more complex than microcomposites. They have multi-phase, at least the faces should have dimension in the range of 10 to 100 nanometers. Figure below shows the types of nanocomposites. The application of nanocomposites. In general, food, biomedical, electroanalysis, energy storage, wastewater treatment, automotive, and other sectors have all used nanocomposites. This comprehensive overview covers the chemistry, architectures, advanced applications, and latest advancement in biorenewable nanocomposites. The example of nanocomposites applications: A. Thin film capacitors for computer chips. B. Solid polymer electrolytes for batteries. C. Automotive engine parts and fuel tanks. D. Impellers and blades. E. Oxygen and gas barriers. And lastly, food packaging.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haris bin Mazlan. I will talk about the material development about the processing technique. There are 7 conditions for the poly 3,4-ethylene dioxythiophene polystyrene sulfonate. First, the solution must be at the room temperature. Second, 3,4-ethylene dioxythiophene as the monomer. PSS as the doping agent, potassium supersulfate, KPS as oxidant, deionized water as the solvent yield. The PEDOT or PSS solution is dark blue in color, 2.2% of solid content, and the pH is the 1.5. The bar coating at a 40% relative humidity and the temperature is at 20 degrees Celsius. The diagram below is the chemical structure for the polytrifluoroethylene dioxythiophene polystyrene sulfonate. Okay, for silver, there are four synthesis methods. First method is using sodium borohydrate and ascorbic acid 99% as the reducing and stabilizing agent. Silver nanoparticles were obtained from the injected sodium borohydrate into silver nitrate. Okay, for the second method, using PVP as a reducing and stabilizing agent. Okay, the third method for silver is using DMF as the reducing agent. The fourth method for silver is the green method. Green resources included plant extract, bacteria, and also enzyme. Okay, for the thermoplastic polyurethane (TPU), there are two stages. The first stage is the reaction between the HMDI and the PTMG to obtain the pre-polymer DI. Okay, this second stage is the two isocyanate function of DI react with chain extender EX to produce the black polyurethane. Okay, that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haziq bin Hazani. For the next part is specific test method including the testing procedure. The first one is tensile test procedure. Tensile testing were carried out with the help of mini Instron 55 tensile tester. For 50 cycles, the samples were strained to 10% elongation at 100 mm per minute. In the Blue Hill 3 program, a macro was used to automatically return to and start the mini Instron 55 test. This enabled the test to be rerun every 10 seconds. The resistance change over the repeated stress was measured using an elegant 34405A multimeter and an HP6186C DC current source. The resistance was measured using the 4-point probe method, which involved generating a 10 mA current while monitoring the voltage change with a voltmeter. Using the current and voltage, the resistance was estimated. The resistance was measured using the multimeter USB connection and a MATLAB program. The next one is band test procedure. The resistance between the terminals was measured using a digital multimeter prior to assembling the band test samples for testing. The band tests were then set up by folding a sample in half with the print on the exterior and clamping one end to a table. Two copper stripes were linked to both terminals between the clamp and the sample, forming a 4-point probe test similar to the tensile test. Before beginning the test, the resistance was measured and compared to the resistance obtained with the digital multimeter. A steel rod with a diameter of 2 mm was put into the fold. The sample was then pressed with a 13 mm diameter rod by rolling it towards the 2 mm diameter band. The sample would be bent at a radius of 1 mm when the roller could no longer roll freely. When the roller rolled back, the pressure was released and the sample returned to a natural bend radius greater than 1 mm. This was done 25 times for each sample, with 5 seconds of pressure and 5 seconds without pressure. Resistance was measured for at least a minute after the cycles were finished, just like in the tensile test. Well, or the last one is resistance testing procedure. Substrate was printed at 5.5 bar pressure using a 65-90-65 squeegee. Then squeegee clamps are placed to ensure a uniform print. Following that, the substrate is carefully placed into the dryer to begin the drying process. The substrate was cured using a dryer in this method, and no bending was detected. When the drying process is complete, the substrate is moved to the testing table. The resistance was then measured and recorded, with the result visible on the multimeter. That's all from me. Thank you.
The part 5.2 shows the suitable diagram or picture that the test has been setting up. For the first picture shows the tensile test procedure. Tensile testing will carry out with the help of a mini Instron 55 tensile tester. In the Blue Hill 3 program, a macro was used to automatically return to and start the mini Instron 55 test. This enables the test to be rerun every 10 seconds. For the second picture shows the band test procedure, which is the resistance between the terminals was measured using a digital multimeter prior to assemble the band test sample for testing. The band tests were then setting up by folding a sample in half with the print on the extrayer and clamp one end to a table. For the last picture shows the resistance testing procedure. The substrate was cured using a dryer in this method and no bending was detected. When the drying process is complete, the substrate is moved to the testing table. The resistance was then measured and recorded with the result visible on the multimeter. So that's all from me. Thank you.
Next, we proceed with theoretical formulation to obtain specific mechanical properties. For tensile test, we can obtain stress, strain, and Young modulus. Formula of stress is F over A, where F is force and A is area of the test specimen. The unit for stress is Pascal or Newton per meter square. For strain, we can obtain by dividing the length of stretch and the original length of the test specimen. There is no unit for strain since it is a ratio of two lengths. For Young modulus, we can obtain Young modulus by dividing stress with strain, and the unit for Young modulus is Newton per meter square. Next is for bending test. When load is applied to the test specimen, the deformation can be determined by the formula below. And then we assume that n is independent of the strict coordinate s, but n is dependent on applied load f. We can obtain the formula below. However, we need to utilize the boundary condition theta 0 equals to theta 1. And then we can obtain strip deflection omega by integrating the equation above. The axial strain can be expressed by the formula below, where u is the displacement in x direction. And then the linear elastic constitutive relation gives the formula below. This can be used to evaluate the axial load N from the applied load F. When the initial stress is present in the strip, we can estimate the effect of the initial stress by adding the initial stress to the axial load N.
Lastly is the conclusion. In conclusion, stretchable conductive ink technology has shown a great promise in many areas, such as enhanced diagnostic, wearable, healthcare, soft robotic, and long-lasting human-machine interfaces. Stretchable conductive ink could be a great revolution in the future. This technology will bring new frontier in traditional design by capturing people's attention through interaction with the environment. One of the advancements in this stretchable conductive ink technology is that it can be used to mimic the function of human skin, and it may be further strengthened by converting human skin stimulation such as pressure, temperature, and many other factors to electrical impulse. This stretchable conductive ink can interface with the human body, and it is compatible with the human supply and sensitive nerve. Last but not least, the most tough challenges in the development of stretchable conductive ink are achieving a great mechanical and electrical performance at the same time. In particular, constituent materials and the devices in stretchable integrated system must be developed to maintain its mechanical and electrical performance under extreme strain. Overall, stretchable conductive ink technology is not meant as a replacement for microelectronic manufacturing, but it is provides an opportunity to produce large area of flexible electronic devices at a low cost. That's all from our group. Thank you.